Take 4. Good grief. Anyway, this is Carl Laterza coming to you from the Mount Juliet Library. And what we're going to be doing is we're going to do a continuation of our series on plate tectonic activity. And if you remember the last time we were together, we saw that all plate tectonic activity is going to originate over here in the asthenosphere because that's where the convection currents are going to be. These convection currents are going to move the plates directly on top of it. And the direction that the plates are going to go is going to be dependent upon the convection currents that you're going to see underneath. Now, these plates can do either one of 3 things. They can diverge, meaning that they're moving in different directions. Divergent plates move in different directions. They can converge, meaning that they are going to collide with each other. Converge, CO, collide, CO, that's convergence. And then the other one is subduction. Subduction is going to be based upon density, which we'll talk about in a couple of minutes. But what's going to happen is one plate is going to go underneath the other plate. All 3 of these actions that we're talking about are dependent upon the convection currents that are underneath. So for example, you see over there on the left, in orange you've got the direction of the convection currents. Then in brown you can see where the plates are. They are moving apart, they are diverging. We saw last week that Iceland is sitting directly on top of a divergent plate, and those mountains that you see over there in the picture, at one time they were connected with each other, but as a result of the convection currents underneath, they diverge, and it's creating that rift valley that you see in between over there. As they split apart, magma from underneath is going to seep into where the area is now ripped. That's going to create brand new crust. We see this as a result of seafloor spreading. Remember we were talking about the Alvin, which now had the ability to go down to the bottom of the ocean and actually see the seafloor spreading at work. Those areas that we see, those dark ridges that we see in the ocean areas, those are called mid-oceanic ridges. Those are going to be areas where the plates diverge, the magma came up from underneath, and it literally piled up. And what we're seeing is we're creating oceanic mountain ranges underneath the ocean. How cool is that? When that happens, that's going to create mild to moderate earthquake activity. Now, they can converge with each other, and if it's the same type of crust like we see over there in that picture, you see the Indian subcontinent gradually migrating across the millions of years to a point where it's going to collide with the Eurasian plate. And because they are the same density, they are going to push up, and that's going to create the Himalaya Mountains, which is a form of orogeny. Orogeny is mountain building as a result of plate tectonic activity. Oh man, this is bad stuff. Over here, we see oceanic crust colliding with continental crust. When that happens, one goes underneath the other, it pushes the ground upwards, and that's really bad stuff. That's where you're going to see your severe earthquake activity, your severe volcanic activity, which in turn will trigger tsunamic activity as well. For example, there's the earthquake of 1964 in Alaska. Over there you've got the tsunami activity in the Indonesian area, which was the result of plate tectonic activity in the Indian Ocean. And there you've got Mount St. Helens erupting over there. The one thing that all 3 of those areas share in common with one another is they're all part of something that we call the Ring of Fire. The Ring of Fire is going to be a collision between oceanic crust and continental crust. The oceanic crust is going to be the Pacific Ocean. The continental crust is going to be North or South America, Asia, or it's going to be Australia. Wherever they collide, because of differences in density, one plate will go underneath the other. Now, these differences in density is going to be the difference between oceanic crust and continental crust. Okay, density. Density tells us how tightly the atoms of matter are packed together. Oceanic crust has a density of 3.0 grams per cubic centimeter, whereas continental crust, which is made up of granite, has a density of about 2.7 grams per cubic centimeter. The rule is, when two substances of different density collide with each other, converge, what's going to happen is the substance with the greater density will subduct or go underneath the one with the lower density. So that means when the basalt of the oceanic crust collides with the granite of the continental crust, the ocean goes underneath, violently pushing the continental crust upwards. This is going to be another form of orogeny. So for example, take a look at the map over there of South America. What you have over there is you've got the Pacific plate colliding with the continental plate, meaning the South American plate. And when they collide, the oceanic crust is going to go underneath and it's going to push the continental crust upwards. The end result is going to be the Andes Mountains. Now, if we go to the Rockies in both the United States and Canada, the same exact process is happening. It's going to be the Pacific plate colliding with continental plate. In this case, it's going to be the North American plate. But the end result is going to be the same. As a result of that, we're going to see orogeny, mountain building as a result of plate tectonic activity. Okay, so where are we now? We've done 3 different types of plate motions: divergent, convergent, and subductive. The last one is what we call lateral plate activity or transform plate activity. Now, this is kind of hard to explain. What you've got is you've got 2 plates that are going to be going side by side, hence the term lateral. When they go side by side, they usually get hung up. And when they get hung up, what's happening is there is a tremendous amount of potential energy waiting to be released. Okay, imagine you're over there, you're going to pull out a drawer, and the drawer's getting hung up, and you're pulling really, really hard, and then all of a sudden, bam, it releases all at once. Well, what's happening there is you've got potential energy as you're trying to pull the drawer apart, and then when it finally releases, that's kinetic energy. Well, when these plates are pushing against each other, there's your potential energy, and when it finally releases, there's your kinetic energy. That kinetic energy is going to be the earthquake. We saw a perfect example of this in 1989 in the 3rd game of the World Series. It was played between the San Francisco Giants and the Oakland A's. Both San Francisco and Oakland are sitting directly on top of the San Andreas Fault. And in the 3rd game of the World Series, the San Andreas Fault decided, I'm bored with the game, I'm going to change things around. Boom! The plate is suddenly going to shift. That potential energy is going to be transformed into kinetic energy. That's going to release a tremendous earthquake. That earthquake is going to be 6.9 on the Richter scale, which brings us back to where we started. You see all of those black lines? Just like we said at the very beginning, all of those black lines represent earthquake and volcanic activity. Why do they represent earthquake and volcanic activity on those lines? Because those lines represent faults, area where the plates are moving one way or the other. And when those plates move, it's going to create earthquake or volcanic activity. Hokey smoke. Wherever you see black, that means that the plates are moving. These plates are creating earthquakes, volcanoes, and tsunamis, just the same as this man said in the year 1912. Dr. Wegener was way ahead of his times and took a while for the rest of the world to catch up with him. Good job, Alfred. That's it.